Let us study about the design for shear. In this class, we will study about the stresses in a homogeneous rectangular beam, the important cases and the potential crack patterns associated with such beams. Then we study about the behavior of reinforced concrete structures when subjected to shear and the important mechanisms involved, including the parameters of design, important terms, and the caudal provisions associated with it. First, let us study about the important stresses which develops in a homogeneous rectangular beam. What do you mean by homogeneous rectangular beam? It is an idealized beam which is composed of only one particular material. It is a homogeneous beam. It has properties the same throughout it. Okay, so we have already studied about the homogeneous rectangular beams when subjected to bending and the important stresses which develop in such beams. In your subject on theory of structures, you have studied what are the important stresses which develop in such beams. They are bending stress and shear stress. So in the basic mechanics of material, we find that any homogeneous rectangular beam will result or will develop two kinds of stresses. One is bending stress, or we call it as flexural stress, expressed by the letter F suffix X. Okay, and there is also shear stress which develops in the beam, which is represented by the notation tau. Okay, so every beam when subjected to loads will develop both bending stress or flexural stress as well as shear stress. You have already learnt about the equations being derived associated with them for the bending stress Fx and for the shear stress tau. So these are the equations. You are already familiar with it, which you have already learnt in the subject theory of structures. So you know how the stress distribution also varies. For bending stress, the stress distribution is linear. We call bending stress as normal stress because they manifest as normal stress only. The fibers will be subjected to normal stress only. So bending stress is inferred by the term normal stress itself. And we have shear stress. The shear stress distribution is parabolic and is decided by these equations. Okay, so every homogeneous rectangular beams, we know that they develop bending stress as well as shear stress when subjected to external loads. So see, here we have a beam when subjected to loads, and you take any point on the beam and just zoom it in, you will find that this point will develop the bending stress Fx, or otherwise we call as normal stress Fx, and shear stress tau. Okay, and we know that a combination of both bending stress and shear stress is acting at this particular point. Okay, and if we resolve it such that we get stresses which are perpendicular to the planes or normal in nature, we call them principal stresses. So you have already learned about principal stresses. The principal stresses are stresses which are normal in nature. These stresses are normal stresses, they are not shear in nature. So the planes in which principal stress acts, they don't develop shear stress. Okay, so instead of a combination of bending stress and shear stress, we are replacing this element by another element which is subjected to principal stresses F1 and F2 only. Okay, and whatever is the effect of these combination of bending stress and shear stress, the same is generated by these set of principal stresses F1 and F2. And you might remember that we had two types of principal stresses. One is a major principal stress, another is the minor principal stress. So this is exactly what we represent by the letter F1 and F2. Okay, and you can observe that these principal stresses F1 and F2, they are opposite in nature. F1 is tensile in nature while F2 is compressive in nature. Since F1 is tensile in nature, we call it Ft, and since F2 is compressive in nature, we call it Fc. Okay, and now you can determine, just like you determine the principal stresses for this particular point on the beam, you can find the principal stresses everywhere on this beam. Okay, and once you find the principal stresses and their directions, you can draw what is known as principal stress trajectory. And principal stress trajectory is the line joining the line giving details of the direction in which the principal stresses are acting. Okay, so trajectory represents the lines which represent the direction in which the principal stresses are acting. So here you observe this point, you have determined the principal stress both Ft and Fc. One is compressive in nature and another is tensile in nature, and you observe that here at this point we have drawn both principal stress as well as compressive stress, the tensile stress as well as compressive stress, both are principal stresses. Okay, and this principal stress which is compressive in nature, you are drawing the directions or the trajectory or the line joining the direction of principal stresses are expressed using a solid line for compressive principal stress, and for tensile principal stress you are using a dashed line to express its trajectory. Okay, so here you are seeing this beam on which we have drawn the lines which represent the direction in which the principal stresses are acting. The solid lines represent the compressive principal stresses and dashed line represents the tensile principal stress. So till now it is clear to you. Okay, now you know that concrete, if this beam is completely made up of concrete, just imagine, we know that concrete is very weak in tension while it is strong in compression. Okay, so which lines are most important to you? We know that since concrete is weak in tension, these dashed lines represents the principal stresses which is tensile in nature. So we should be very much afraid about these dashed lines. Okay, because these are the directions along which tensile principal stress is acting. Okay, now what happens when tensile stress acts on this particular point? This point is experiencing tensile principal stress in this direction. As a result, how does the crack occur? Crack occurs in the direction perpendicular to the direction of stress. You know it very well. If you have a paper and you hold it and stretch it on either sides, you see that the crack develops perpendicular to it, isn't it? So just like that, tensile stress is acting in this direction and this will develop crack in the direction perpendicular to it. So what is the direction which develops cracks? It is the same as the direction of the solid principal stress, or these solid principal stress trajectories, or they are compressive in nature, but they actually show the direction in which, or they are the ones which indicates the potential crack patterns which you see in this figure. Okay, so cracks are likely to occur in a direction which is perpendicular to the direction of tensile stress, and that direction is nothing but the direction of compressive principal stress. And if you observe, These compressive principal stress directions are important because they represent the potential crack patterns. So if such a load occurs on the beam has high chance to develop cracks or failures in a direction which is given by principal stress trajectory of compressive in nature, compressive principal stress. Okay, so this is the potential pattern of cracks which can develop in such homogeneous rectangular beams. Okay, now we need to know how the concrete behaves under shear. So we have already studied that any beam when subjected to loads will develop bending stress as well as shear stress. What happens when the beam experiences bending stress? We have already studied about the design of beam when subjected to flexure or bending, and we have designed such beams for bending moment. But now we need to study how to design a beam for shear stress. Okay, so that is exactly what we are going to learn. But before we proceed further, we need to know how are the ways the reinforced concrete undergoes failure or cracks. So what are the different modes of failure or cracking? There are 4 important ways in which cracks can occur in reinforced concrete structures. First one is flexural crack. You see this figure? These are typical flexural cracks. These cracks are likely to occur in beams where high bending stress occurs and low shear stress occurs. So those beams in which bending stress is high and shear stress is low, such beams experience flexural cracks like this. The speciality of the cracks is that they develop at extreme tension fibers and they propagate towards the neutral axis. And in which direction? It is propagating at a direction 90 degree to the neutral axis. Okay, it is propagating at direction 90 degree to neutral axis. And what should we do to arrest such cracks, which we have already learned? Since we know that concrete is very weak in tension, we have provided tension reinforcements. These reinforcements are being provided on the tension side, and these reinforcements are effective in resisting or arresting the cracks which develop due to high bending stress, or the flexural cracks are arrested with the help of tension reinforcements. Okay, now coming to the second type of crack, which we call it as diagonal tension crack or web shear crack. These kind of cracks, so the previous one was flexural crack, now we are talking about shear crack. Okay, flexural crack occurred when high bending stress occurred. Now shear crack or web shear crack or diagonal tension crack, these occur when the beam experiences high shear stress. Okay, when high shear stress occurs in beams, especially in case of deep beams and those beams subjected to heavy concentrated loads where shear stress is very high in beams, in such situations we find that web shear cracks or shear cracks occur in such beams. And what is the location of such cracks? What is the speciality of such cracks? They occur at a region in the vicinity of neutral axis. They occur at a region closer to the neutral axis. Unlike the flexure crack, which is occurring away from the neutral axis and propagating towards neutral axis, these shear cracks develop very near to neutral axis. And what is the direction in which they propagate? They propagate in a direction 45 degree to the longitudinal axis of the beam or 45 degree to the neutral layer. Okay, and how to resist them? We need to provide shear reinforcements to resist such shear cracks. Okay, so we provide those set of reinforcements which are being provided to resist shear cracks are called shear reinforcements. So we need to design shear reinforcements and provide them such that shear cracks or web shear cracks are arrested. Okay, now coming to the third set of cracks, we call it as flexure shear cracks. Flexure shear cracks is very simple. You just have to combine the previous two types of cracks. You have flexure crack and here you have shear crack. The combination of both will give you flexure shear crack. So those cracks occur in beams subjected to both flexure stress as well as shear stress. So those beams where flexure stress as well as shear stress are substantially higher, flexure shear cracks occur. And the way they propagate is also a combination of the both. Initially, the flexure crack develops at the extreme tension fiber, which is nearly perpendicular to the neutral axis. And as they propagate further near the neutral axis, they tend to incline and achieve an angle closer to 45 degrees and become a shear crack. So initially it is a flexure crack and later it becomes a shear crack. So a combination of both will give you a flexure shear crack. Okay. Now coming to the fourth case of crack, which we call as the secondary crack or splitting cracks. You see, we have a flexure shear crack here. In addition to this crack, there occurs cracking or splitting along the tension reinforcements provided. Okay, along the tension reinforcement provided. And why does it happen? The possibility for such cracking along the longitudinal bar is due to wedging action or double action. So by wedging action, what we mean is that here the flexure shear crack has occurred and this crack has split the beam into two. There is one segment here and another segment on the right side of the crack. As the right side of the crack tends to move down, it tends to exert some stress through the reinforcement and tends to wedge away the reinforcement away from the segment, and this results in a propagation of crack, which is what is known as wedging action. What is double action? Double action is that as this segment moves down, this tends to pull the reinforcement away from the first segment, and that may also result in splitting of concrete closer to the tension reinforcement. So this we call it a splitting crack or secondary crack. Now, since we are interested only in the mechanism by which the shear gets transferred in beam, because in this class we are going to study how to design a beam for shear, we are going to study about the shear transfer mechanism. So what are the different ways by which shear stress is resisted by our reinforced concrete member? You see this figure. Initially, the concrete undergoes a crack at the extreme tension fiber, which is what we call as the flexural crack. But as you keep increasing the load, the crack moves on closer to the neutral axis. It inclines and becomes 45 degree. Okay, and it is now a shear crack. So overall it is a flexure shear crack which we obtained. Now in this situation, how is the shear getting transferred by the beam? We know that a part of concrete on the compression side is still not cracked. Okay, so this part of concrete which is uncracked, this will help to resist shear somewhat. So this is what we call as the shear resisted by uncracked concrete, the shear resisted by uncracked portion of concrete, which is represented by the notation V suffix C. Now since this part is resisting a part of shear force, there are other parts also which is also capable of resisting shear. You know that this crack has occurred, okay, and this has divided the beam segment into two. There is one portion on the left side of the crack, there is another portion on the right side of the crack. As a result, there is a relative movement between the two segments. The first segment will move, or the second segment will move relatively with respect to the first segment. As a result, there occurs an aggregate interlocking at the interface of this crack. Okay, at the interface of this crack, interlocking or frictional resistance will be offered by the aggregates of the concrete between the two segments, and this will also resist shear. So that we call as the shear resistance by aggregate interlocking along crack interface, represented by the notation V suffix A. Now this is not yet over. The next one which resists the shear is the double action by the tension bar. You know that the longitudinal main bar is passing through the tension side of the reinforced concrete beam, and it connects one segment to the another, and this bar is also subjected to shear, and this bar is also capable of resisting shear. So that is exactly what we call as the double action of the tension bar, represented by the notation VD. Okay, and this is still not over. If we are providing what are known as shear reinforcements are provided in the direction perpendicular to the longitudinal bars. If these shear reinforcements are provided, the crack which occurs as flexure shear crack, as it propagates further, the shear reinforcement is likely to arrest the propagation of these cracks closer to the neutral axis. Okay, so shear reinforcement is also responsible for resisting the shear force. Okay, so what are the different methods by which the shear stress is resisted by the reinforced concrete beams? One is the uncracked portion of the concrete, second is the aggregate interlocking, third is the double action by tension bar, and fourth is the shear resistance by shear reinforcement. Okay, just have to bear these factors in mind. And how is exactly the shear getting transferred? The sequence of events is also explained here. So as you apply load here, the entire section is capable of resisting the shear force because it is not cracked anymore. So you keep increasing the load, you find that the crack occurs at the tension side of the beam, which we call it as flexure crack. So once flexure crack occurs, the crack is initiated and some shear gets resisted by the double action of bars as well as due to aggregate interlocking between the two segments. Okay, and you keep increasing the load, the crack also propagates further until it reaches the shear reinforcement provided here, so that a part of the shear force is also resisted by the shear reinforcements. Okay, so this is exactly what happens as you apply the load, and this is exactly how the shear force is getting transferred in the reinforced concrete beam. So one thing to be kept in mind is that these shear reinforcements play a very important role to ensure that the shear failure is gradual and ductile. So for which case we need shear reinforcement. Shear reinforcement ensures that the shear failure is ductile in nature. Okay. Now coming to the important parameters of design. Here we will be familiarizing you to important terms used in the design. So first important term is nominal shear stress, expressed by the notation tau V, tau suffix V. So bear it in mind, tau V is the nominal shear stress. In simple terms, tau V is the shear to be resisted by the beam due to externally applied loads. You know that if you refer to page 36 or 37, you will find these set of figures and the relevant caudal provisions. You will find what are the critical sections for shear. What are critical sections? You know that every beam, when subjected to loads, will develop shear force, and the distribution of shear force along the span is known as the shear force diagram. You know how to draw a shear force diagram. But what is the value of shear force to be chosen for the purpose of design? So for which IS code has given these recommendations? I am saying, like, for the time being we focus only on the simply supported beams. For simply supported beams, if this is the support at a distance d away from the support, where d is the effective depth of the reinforced concrete beam, at a distance d away from the support, you consider the section. The shear force at that section is the critical value of shear force to be used for the design. We represent it by the notation V suffix U. Okay, and that value of critical shear force VU due to externally applied loads divided by B into D, where B is the breadth of the member and D is the effective depth. This will give you the nominal shear stress tau V. So if in the examination you are given the external load on the beam, you can easily find the value of shear force acting at a distance D away from the support. You just have to divide VU divided by BD to obtain the nominal shear stress. Okay, so tau V, it is a nominal shear stress, and it is the shear stress developed due to externally applied load. Now coming to the next important terminology, that is the design shear strength of concrete, that is tau C. What is this tau C? Tau C is the maximum shear stress that the reinforced concrete beam can resist without shear reinforcement. So even without the shear reinforcement, we already told that in the mechanism of shear transfer, shear reinforcement play a very important role. They ensure gradual and ductile failure of beam in when subjected to shear. Okay, so shear reinforcement is very, very important. But if without shear reinforcement, what is the maximum shear that the beam can resist? So that is exactly what is given by the parameter design shear strength of concrete tau C. Okay, so how do you find tau C? Tau C value as per page number 72, clause 40.2, you see the design shear strength of concrete in beams without shear reinforcement is given in table 19. Okay, table 19 is there in page number 73, the next page of which, from which you can get the value of tau C. Tau C is very simple. Here is given 100 AST by BD. This is the percentage tension reinforcement used in the beams. And here is given the concrete grade. So you just have to choose the appropriate grade of concrete from this table corresponding to the percentage tension steel. You can easily determine the value of tau C. So tau C, or the design shear strength of concrete, is nothing but the maximum shear stress which the beam can resist without shear reinforcement, and can be obtained from this table 19 on page number 73. Okay, now how to design for the shear reinforcement? What happens if tau V is less than tau C, or what happens when tau V is greater than tau C? We know that tau V is the stress developed in beam due to externally applied loads, and if it is less than tau C, where tau C is the maximum stress it can resist without shear reinforcement. Okay, so this is the maximum stress the beam can resist without shear reinforcement, and if the applied stress is less than the maximum stress without shear reinforcement, do you actually need a shear reinforcement? No. So since tau V is less than tau C, you don't require to design shear reinforcement. However, in certain situations we provide minimum shear reinforcement for certain kinds of members, about which we shall see in the coming slides. So what you have to bear in mind is that if the applied shear stress is less than what actually can be resisted by the beam without shear reinforcement, you don't actually require shear reinforcement at all. Okay, now but if tau C or tau V is greater than tau C, if the applied shear stress is greater than the maximum stress which can be resisted by the beam without shear reinforcement, then you require shear reinforcement, and shear reinforcement must be designed in such situations. Okay, now for your understanding, please bear in mind that the shear strength of slab is greater than that of beams. Why? We know that slab is a very thin member. It is very small in thickness. Because of its smaller thickness, when you subject it to loads, the development of shear stress is very, very low. It undergoes more of bending than developing shear stress. So that is exactly the reason why slabs develop less shear stress than bending stress, and because of which a factor K has been added as per this clause 40.2.1.1. You see, for solid slabs it is not just tau C, you have to multiply it with the value K, and the value of K is also given here. So as you increase the thickness of the slab, the value of K is decreasing, or in other terms you can say, as the depth of slab is decreasing, the K value is increasing, which means that the capacity of the slab to resist shear stress is more if the thickness of slab is very low. So for smaller or thinner slabs will have more shear resistance than thicker slabs. Okay, so that is exactly the reason why we don't require shear reinforcement for slabs. We design shear reinforcements only for beams, and for slabs we generally don't design for shear reinforcements. Now the third important terminology is this: the limiting ultimate shear resistance of beam, given by tau c max. So we learned about tau c, which is the maximum stress that the beam can resist without shear reinforcement. But even with shear reinforcement, what is the maximum shear stress the beam can resist? So that is tau c max. Okay, so we learned about tau e, we learned about tau c, and now it is tau c max. So tau c max is the maximum shear resistance the beam can resist with shear reinforcement. Even with shear reinforcement, this is the maximum shear that can be resisted by the beam. But we must wonder why we need to have a maximum shear stress even with shear reinforcement. Why do we have a maximum shear resistance of beam? This is because of the following reasons. We know that we might feel that as you increase the shear reinforcement, the maximum stress that the beam can resist will also keep increasing, isn't it? But it is not just so, because if you keep increasing the shear reinforcement, the beam loses its ductile nature. So when we studied about the over reinforced section, we already learned that with a lot of steel reinforcement, the over reinforced section, that is exactly why we call it over reinforced section. So with a lot of steel reinforcement, a situation might arise where the over reinforced section will behave in such a way that concrete crushing occurs well before yielding of steel. So it is an undesirable section. We know that due to lot of steel, the steel doesn't yield, but crushing of concrete occurs. But crushing of concrete occurring before yielding of steel is undesirable. Why? Because it doesn't give warning to the user. So similar way here also, with excessive of shear reinforcement in the section, the beam loses its ductile nature, and as a result the crushing of concrete occurs before the yielding of shear reinforcement, and we call such a failure as shear compression failure. This failure is not desirable at all. So that is the reason why we have to limit the use of shear reinforcement in beams, and there in order to resist or in order to limit the amount of shear reinforcement in the section, we are defining a term tau c max. So tau c max is the maximum shear stress that reinforced concrete beam can resist with shear reinforcement. Even with shear reinforcement, what is the maximum shear that it can resist? And we must always satisfy a condition that the beams being designed will have tau v is less than tau c max. In no condition the applied shear stress exceed tau c max, then this will result in complete failure of our beam. Okay, so under no circumstance tau v should exceed tau c max. So tau c max should be the maximum. Never tau v can exceed tau c max. Okay, so where do you obtain tau c max? It is easy. Refer to page number 73. You will find table 20. Directly corresponding to each grade of concrete, you have the value of tau c max. Okay. Now coming to the design of shear reinforcements, you must know what are the different ways by which you can provide shear reinforcement. Just see this figure. These loop-like reinforcements being provided, we call it shear reinforcement. Shear reinforcements may be provided in any of the following ways. First, stirrups perpendicular to the beam axis. So that is exactly what is given here. Stirrups provided perpendicular to the beam axis. We call it vertical stirrups. So stirrups is another term for shear reinforcement. And what are the different ways by which stirrups can be made? That is exactly what is shown here. It can be made in the form of a loop like this, in the closed form, or in the open form like this. Okay, these are the different ways, and we call these set of stirrups as two-legged stirrups. Two-legged means it has two vertical legs like this. Each stirrup has two vertical legs like this. Okay, that is why we call it as two-legged stirrups. And there may be stirrups inclined at 45 degree or more. That is exactly what is shown here. These inclined stirrups are those stirrups, shear reinforcements provided at some angle 45 degree or more. Okay, you can also provide shear reinforcement in the form of longitudinal bars bent up at 45 to 60 degrees to beam axis. So that is exactly what is shown here. You see these bent up bars, we call them bent up bars. These bent up bars are also capable of resisting shear cracks. Okay, so longitudinal bars may also be provided, but one thing to be made sure is that they should be used along with stirrups. They should not be used just themselves. They should be used along with stirrups. You cannot use merely bent up bars for resisting shear. You have to use a combination of both. Okay, you can either use stirrups as such, or if you are using bent up bars, you have to use at least more than half of the stirrups to resist the shear. So that is exactly what is given here. For the total contribution towards shear resistance, if bent up bars are provided, at least half or more than half should be due to stirrups, and only less than half should be the contribution by the bent up bars. Okay, now coming to the caudal provisions for shear design, how to provide shear reinforcements. So we have learned that if tau v is greater than tau c, we must know that tau v is the applied shear stress, the shear stress due to applied force, and tau c is the maximum stress which the beam can resist without shear reinforcements. So if we said if tau v is exceeding tau c, definitely we need shear reinforcements. And how to provide it? As per page number 73, clause 40.4. So there you will see a set of equations like this. So what is the shear force to be resisted by the stirrups? You know that Vu is the maximum shear force that the beam is subjected to. So this is the design shear force Vu. Okay, and that Vu, the entire Vu is resisted. The entire Vu is resisted partially by the uncracked section of concrete and partly by the other reinforcements, including shear reinforcements. So we know that tau c into BD, the tau c into BD is exactly what is being resisted by the uncracked portion of the concrete. So this is the total shear force to be resisted, and from which you are subtracting what can be resisted by the uncracked portion of the concrete. The remaining should be resisted by the stirrups. So that is why we write this expression VUS is equal to VU minus tau c in BD. This is exactly the shear force to be resisted by the stirrups. So you don't have to by heart these values. It is available in the page number 73. Okay, so once this is determined, you can use the next set of equation, that is VUS is equal to 0.87 Fy ASV into D by SV, where Fy is the yield strength of steel, which you know. What is ASV? ASV is the cross-sectional area of the stirrup legs. Okay. For example, we are using two-legged stirrups, so of diameter 5. Then instead of n, you substitute 2. So 2 into pi by 4 into 5 square. Okay, will give you the value of ASV, the cross-sectional area of the stirrup legs, both the legs. So if it is n-legged stirrups, it is n into pi by 4 5 square. Okay, now small d is the effective depth, which you know. So VUS you obtained it from the previous equation, so substitute it here. So you, in this equation, in this particular expression, you know everything except SV. What is SV? SV is the center to center spacing of stirrups along the length of the member. So between the adjacent stirrups, you see here, between the adjacent stirrups you have center to center spacing between the stirrups. So this you have to find out. Okay, this you have to find out. Now phi value, if it is not given in the question, you can assume a suitable diameter of stirrup. Generally 8 mm diameter stirrups are used. So if everything else is known, you can determine SV value. Okay, so this is the spacing, center to center spacing between stirrups. And one thing to be noted is that for vertical stirrups, there is a limit to which you can provide the spacing of stirrups. The maximum spacing between stirrups should not exceed 0.75 times effective depth or 300 mm, whichever is minimum. Okay, so the maximum spacing between the stirrups, adjacent stirrups, is 300 mm or 0.75 d, whichever is minimum. You can refer to this clause on page number 47 for reference. Okay. Now what happens if tau v is less than tau c? We said the shear stress to be resisted due to the shear stress due to applied force is tau v. So if it is less than tau c, the maximum that can be resisted without shear reinforcement, then we said normally we don't require shear reinforcement at all. Okay, if tau v is less than tau c, we don't require shear reinforcement. But in certain situations we have to provide shear reinforcement, but minimum shear reinforcement is provided. Not as we designed in the previous case, we will provide shear reinforcement only to a minimum requirement. How? So for which case we need to consider two cases, where if tau v is less than even 0.5 times tau c, in such situation the tau v value is very, very small and you don't have to design for shear reinforcement at all. Okay, but in situations where tau v is exceeding 0.5 tau c, although tau v is less than tau c, it is greater than 0.5 tau c, then you have to provide minimum shear reinforcement based on this equation. This equation is available with this page 48, clause 26.516. In this equation, it is ASV by BSV is greater than or equal to 0.4 by 0.87 Fy. Here ASV value, you know how to find it out, it is already given here. B value is width of the beam. And what is SV? SV is the spacing. So you know everything else except SV. So what you have to do is you bring SV term to the right hand side and every other term on the right hand side to the left hand side. Okay, so on the right hand side, if you are left with SV, that will give you SV is less than or equal to some value. Okay, so that will give you the required spacing. What is the maximum spacing that can be used in such reinforcements? Okay, such beams for shear reinforcement. Okay, so that is how exactly you provide minimum shear reinforcements in beams. So again, you have to keep in mind the maximum spacing between stirrups should not exceed 0.75 d or 300 mm, whichever is minimum. This is applicable to this case also. Okay, so now we will solve a couple of numerical examples and you will get a better grasp of it now, right now.